Okay, let's use the localized electron model to fully describe the bonding in acetylene. Acetylene has the formula C2H2. It's used as a fuel in blowtorches and things like that, for welding, for example. C2H2 is going to give me 10 electrons that are available. And I can build this molecule by constructing the sigma skeleton. I'm going to put one H on each of the carbons, and I'm going to bond the carbons to each other. In doing that, I spent 6 out of the 10 electrons. So the only place for me to put the other 4 electrons is in between these 2 carbons. So here's the Lewis structure for acetylene. Notice that acetylene has a triple bond. And a triple bond, by definition, is going to be composed of 1 sigma bond plus 2 pi bonds. So let's try to figure out, using everything we know from this chapter, what kind of orbitals and orbital overlaps kind of give rise to those sigma and pi bonds. So we need to look at both carbons, and we can count if their substituent number. They're in identical bonding environments, so we can see that each of them is going to have, so both of them have a substituent number of 2 because they have 2 bonds each. So 1, 2, and then on the other side, 1, 1, 2. That means that I'm going to have 2 hybrid orbitals, 2 sp hybrids. So each carbon is going to have 2 sp hybrids and 2 leftover unhybridized 2p orbitals. So let's draw what that would look like. I am going to draw both of my carbons, and I'm going to draw just big old lobes to represent my sp hybrids. So this is sp and sp on that carbon, 2 sps on that carbon. And for this carbon, I'm just going to use a different color to draw its sp orbitals, sp and sp. So 2 sp hybrids on each carbon. Now, hydrogen, of course, has only its 1s orbital, which is spherical. So I'm going to draw hydrogen's 1s over here, and it's going to be the overlap of hydrogen 1s with carbon's sp hybrid that forms the CH single bond. Now, what else do we have going on? So we've drawn the 2 sp hybrids that each carbon has, but we now need to account for the 2 sp2 orbitals that it has. So in my cartoon here, I've kind of drawn the horizontal axis as the bonding axis, and that's where we have the sigma bonds forming. But each carbon is also going to have these unhybridized 2p orbitals. So I'm going to draw one of them like this. I'm going to label that 2py because it's going in the vertical direction, so along a y-axis. So here's 2py on that carbon, and here's 2py on the other carbon. So that's one of the 2p orbitals on each of the carbons, but I know that each of them has actually 2 2p orbitals left unhybridized. So let's draw those. I'm going to pick yet another color. My drawing's getting pretty complicated now. To draw yet another set of dumbbells. So imagine this lobe going back into the screen and this lobe coming right out towards you. I'm going to label those 2pz, so along the z-axis in 3-dimensional Cartesian coordinates. So now I can use interaction between the 2p orbitals above and below the bonding axis to justify the creation of the pi bonds. So I'm going to have interaction between the lobes of the 2pz orbitals above and below the bond, and I'm also going to have interaction of those 2py orbitals above and below the bonding axis. So these lines that I'm drawing are just showing kind of interaction between those orbitals. So now my cartoon is complete, but I want to also describe what's going on in words in this cartoon to fully describe the bonding in the acetylene molecule. So it's going to be really the overlap of the carbon sp orbital with the other carbon sp orbital that creates the sigma bond. Then the pi bonds are created by the interaction between carbon 2py and carbon 2py. So that's going to create one of the pi bonds. So that's the one that I kind of drew in this magenta color here. Then in the interaction of the one that I drew in the navy blue color is going to make the other pi bond. So it's the interaction between the carbon, what I called 2pz, with the other carbon 2pz that creates the second pi bond. Now remember, a triple bond is one sigma bond plus two pi bonds. So we've accounted for the triple bond, the triple carbon-carbon bond. Okay, so all of that means that the triple carbon-carbon bond is accounted for. It equals 1 pi plus 2, but 1 sigma rather, plus 2 pi bonds. And we've accounted for all of them using our orbitals. The other thing is that, just to be really, really complete, the overlap of the carbon sp orbital with the hydrogen 1s orbital creates each carbon-hydrogen sigma bond. So there we have a full description of the bonding in acetylene using the localized electron model, okay, in both words and pictures.